So it's a great pleasure to have Minha Kwang from RIKEN to give this joint CIS and RIKEN AIP talks. Min is a unit leader at RIKEN AIP, where he leads the functional analytic learning unit. He received his PhD degree in mathematics from Brown University with Stephen Smale. Before joining AIP, he was a researcher at the Italian Institute of Technology in Genova. His current research focuses on functional analytic and geometrical methods in machine learning and statistics. Min will be talking about regularized information geometric and optimal transport distances between covariance operators and Gaussian processes today. And without further ado, take it away, Min.
Well, thank you very much, Volkan, for the introduction. So I will talk, today I will talk about the distances between, as Volkan said, covariance operators and Gaussian processes. Can you hear me well? I think okay, I think you can hear me well. So the talk will be on the generalization of the chemistry of the following geometric structures for Gaussian measures in Rn. To infinite dimensional Gaussian measures and Gaussian processes. So we'll talk about some of the Riemannian distances and divergences and optimal transport distances. We'll talk a little bit about, talk a little bit about the connections and unifying formulations. So kind of this kind of more like a chronological. So this kind of talk, this is what I did like a couple of years ago, and then this kind of more like basic work. So very briefly, we have like the motivation for this study. There's a lot of work on the geometric structures and Gaussian measures on Euclidean space and symmetric positive definite matrices, because they play a central role in statistics and probability and machine learning, and they have like, a lot of practical applications: so brain imaging, computer vision, radar signal processing, brain computer interfaces, etc. So that's actually this is a huge topic. There's a lot of work and a lot of theory and a lot of applications. So now we'll just talk about like a few things. Like let's first talk about some of the Riemannian distances. So the Fisher-Rao metric. So consider the set of Gaussian densities on Rn. So this is so a Gaussian density with zero mean is characterized. So it's given by this formula here. The density is given by this formula here, and it's completely characterized by its covariance metric sigma theta here. So sigma theta is a matrix, it's an n by n matrix, a symmetric positive definite matrix. So it's given by its, so we can parameterize it by a set theta, and since it's symmetric, so it has size n by n, but we just need to go to kind of the to parameterize at the upper half of the matrix. So it has n times n plus 1 of the two parameters. So this is we can parameterize it by a set theta here in Euclidean space, and it's an open set. So it says it has a structure of a smooth manifold, and we can define the Fisher information metric is given by this formula here. So this is actually a very well-known quantity in information geometry. And so this, in this case, it defines a Riemannian metric on S, the so-called Fisher-Rao metric, Fisher information metric. And for this, in the case of the Gaussian density, of course, we can compute this explicitly. So it's a central element in information geometry, and we have an explicit expression for it. It's given by this formula here. And because we have the correspondence between the Gaussian density with zero mean and the symmetric positive definite matrix via the covariance matrix, we can also have we have the Fisher-Rao metric corresponding to something called the phi invariant metric on the set of symmetric positive definite matrices. So it's given by this formula here, and so we have so with this metric now we have the set of SPD matrices becomes and then SPD matrices becomes a manifold, a Riemannian manifold, and so many things can be called. So this is on the phi invariant Riemannian metric has been studied a lot, and we can compute many things explicitly. So for example, we can it's a manifold with negative not positive curvature, so it has a unique geodesic showing any matrix A and B, and this geodesic here has a closed form formula. And also its length is a Riemannian distance. It's given also has a closed form formula. So there's a lot of so basically it's a Fisher-Rao. So It's a half of the physical distance between two Gaussian measures on array. And so a lot of things have been studied about this. And another one is a simple one, is to be a locality metric. So this one is a simple Riemannian metric, and it also has like a unique geodesic joining A and B. So it has a simple form. You know, the geodesic has a simple form, and the Riemannian distance has a simple expression as well. So just log minus log with this norm. And it's faster to compute than the other distance, and one can also define the considerable kernels with this distance, for example, the Gaussian kernels. Because this one is a flat, the manifold under this metric, the manifold is a flat manifold. And so now let's talk about how we can actually generalize this to the infinite dimensional setting of Gaussian measures on the covariant Gaussian measures, so Hilbert space and covariance operator. So in this case, we have an infinite matrix or an operator. So now for this instance, the infinite dimensional generalization will be substantially different from the finite dimensional formulation. And why? Because for an SPD matrix, we can, the log A here is the principal logarithm of the matrix. So if we have the spectral decomposition of A is written in this form, then we to compute the log of A, we just compute the log of the eigenvalues, and we multiply by this matrix U here, which consists of the orthonormal eigenvectors. Now, if A now is an infinite dimensional or like positive operator, which is a covariance operator, for example, then it's a Hilbert operator. So it has infinitely many eigenvalues. So eigenvalues lambda k will go to 0. They will go to 0 as k goes to infinity. So then 1 over lambda k will go to infinity, and log of lambda k will go to negative infinity. So now, in order to compute these things, so this distance here, we need to compute the inverse, then we need to compute the log. So you can see here that with the 1 over lambda k going to infinity, and log of lambda k goes to negative infinity, so the A inverse will be unbounded, log of A will be unbounded. So we do not have a direct generalization to the infinite dimensional setting. So what we can do is let's try to generalize this log distance for this formula log A minus log B with the following norm to the infinite dimensional setting with the self-adjoint positive Hilbert operators on the Hilbert space. So we need to do two things. We need to generalize the matrix, the principal matrix logarithm, and then we need to generalize the fullness in the product. And it turned out that the Hilbert norm is actually not a sufficient quantity. So first, let's talk about the log function, the matrix log function. Now, this is actually so it's given by this formula here, where this UK cancel UK, UK transpose. For the finite dimensional setting, except that we have infinitely many of these quantities, and with the log of lambda k goes to negative infinity. So this is unbounded. So what we can do is regularization. We can add gamma I, where I is the identity operator, where gamma is greater than 0. So if we do this, then log of lambda k plus gamma is always bounded. So when k goes to infinity, just go to log of gamma. So this whole thing is bounded. This over the log of gamma I is bounded. So we solve this problem. So let's move on to the second problem. Now we have log, instead of log A minus log B in this form, we can consider log A plus gamma I minus log of B plus mu I with Hilbert norm. But the problem is actually this quantity is in general is not finite, because the identity operator is not a Hilbert operator. So then because with the Hilbert norm here, the identity will just the trace is equal to the trace of the identity will just equal to infinity. And so if gamma is not equal to 0, then this quantity here, log of the Hilbert norm of log of A plus gamma I square will be equal to infinity. And in particular, the distance between like the two multiples of the identity operator will be equal to infinity. And so to resolve this, the resolution of this is actually something called the extended Hilbert norm. So it was introduced by Larotunga in 2007. So instead of the identity operator, we define this the Hilbert norm as extended Hilbert norm put here the norm square of A plus gamma I square is equal to the Hilbert-Schmidt norm square of A plus gamma square, along with the extended Hilbert-Schmidt inner product. So it is defined in this way so that the scalar operators gamma I are orthogonal to the Hilbert-Schmidt operators. And so if we define it like this, then the extended Hilbert-Schmidt operator is equal to 1. So it's something we call it the kind of a form of compactification. Because instead of infinity, we actually compactify so it's equal to 1. So this is actually a Hilbert. This is now okay. So the generalization of the set of SPD matrix to the infinite dimensional setting is actually Hilbert manifold. So it's actually the set of form. Instead of just A, we have the form A plus gamma I. Equal to 0, where A star is equal to A, and A is the Hilbert-Schmidt, so A star equal to A is the self-adjoint. And so we recover if A is self-adjoint, and the Hilbert-Schmidt norm square just equal to summation of all the eigenvalues square. So Larapunga generalize the affine invariant Riemannian metric. And so the tangent space is just a set of all the symmetric self-adjoint extended Hilbert-Schmidt operator, and then the Riemannian metric just given by this formula here. And the distance is actually quite similar. So the distance is quite similar to the paradimensional case, except that we, instead of A and B, we have A gamma I plus B plus UI, and instead of the Frobenius norm, we have the extended Hilbert-Schmidt norm. So this is the setting for the generalization of the affine invariant Riemannian metric. And we can do this for the log Hilbert-Schmidt metric, for the log Euclidean metric as well. So we can, instead of the log of A minus log B, we can have this distance log plus gamma minus log B plus UI with Hs. And we can compute also the log Hilbert-Schmidt inner product. So this actually, with this something called the log Hilbert-Schmidt metric, we also have, like, as in the same case of the log Euclidean metric, we also have a flat Riemannian manifold. And all quantities are going to be finite because of the extended, because we do the regularization. So there are two things: we do the regularization, and then we do the extended Hilbert-Schmidt norm. So now there are so these distances are kind of abstract distances between abstract operators. So there are at least two ways to compute them concretely in practice. I'm talking about the case that the two cases that inform the reproducing Hilbert spaces of RKHS methodology. The first one is the distances and divergence between RKHS covariance operators. And the second one, which I will talk about later on, is the distances and divergence between Gaussian processes and covariance operators of stochastic processes. And they both involve RKHS methodology. So, okay, I will be quick on this one because this work I did some years ago. So now, let's talk about the first setting with RKHS covariance operator. So if we have a positive definite K and a corresponding RKHS HK, then there's a canonical feature map phi that map X to HK. So we have phi X equal to KX. It is given by this formula here. And so let's assume, so the input product in HK of phi X and phi Y just equal to KXY. And assume that we have a probability distribution rho on X, so that so phi X come norm square with the integral of this is finite, which is equal to Kx, integral of Kx equal X. So this is finite. Then we can, and then we assume that we have a data set X here, that we can do this with M observation X1 up to Xm. Now with this feature map phi here will give informally an infinite feature matrix of phi X and phi X1 up to phi Xm, but formally is another linear operator. So it maps Im to HK. So it's given by this formula here. And so because of this, because we assume that the second moment of phi X is finite, we can compute this the theoretical mean, the mu phi, just the expectation of phi X, the rho X, and the empirical RKHS mean. It's just the average of all the phi Xi, whatever estimation of the phi Xi. So it can be written in this form as well. Now, if we have the linear kernel, for example, on a Euclidean space, then this is mu X here just equal to the just a sample mean of the Xi. So this is which is like, instead of summation of Xi, we just map Xi to phi Xi. And this one will be also just in expected value of X. And similarly, we can define also the covariance operator as well, the RKHS, so it maps from HK to HK. And so this is kind of like Vx plus Vx transpose here, and then this is the empirical covariance operator given the data points x1 up to xn. So it's just a summation of all the Vxi to Vx transpose actually. And then minus is mean times transpose. So it's given in this form. Now in the linear kernel setting, this just becomes a sample covariance matrix of 1 over n. Essentially m x transpose. So sometimes we can actually use 1 over n minus 1 as well, but I'm just going to use 1 over n for simplicity. Now, so if we define so we can define given the kernel, we can define like the covariance, the RKHS covariance operator in this form, and then the distance between the two RKHS covariance operators can be given close form formula, so that is the prime matrices. So we can distance between like CVX plus gamma I and then CVX plus gamma mu I can be given in closed form. So the kernel matrices are given with this like KXI, for example, just KXI XJ. So now, okay, I would not go into the detail of the formula, just to show you that we have closed form formulas in terms of the gram matrices. Everything can be computed in closed form, and so this actually has been applied in some computer vision class. And so this one is actually, for example, a two-layer kernel machine for image classification. So here we start with the images and the features and so on, and then we extract the features and we apply the kernel K1 on top of the features. And since K1 induces a feature map, so we can define like a covariance operator using K1. This covariance operator is defined implicitly, of course. And then we can compute the log. So each image is represented, for example, by one covariance operator. And then we can compute the log image distance between these covariance operators, and we can compute the distance matrix, and we can apply a kernel K2. So this actually has been applied both where everything can be computed in closed form, and then it can also be approximated as well using the random Fourier features. So this is actually one way in which these quantities can be computed, can be applied in practice. So this is the remaining distances. Now we also have divergences. So that's also the convex cone, open convex cone viewpoint with set of SPD matrices. And using this, we can define the log weighted divergences. So we have several families of divergences. This one is commonly called the alpha log divergences. So it's parameterized by a parameter alpha here. So it's given by this formula. But this is in general not symmetric. It's only symmetric when alpha is equal to 1. And alpha equal to 0. Sorry. It's only symmetric when alpha is equal to 0. When alpha goes to 1, it goes to this limit, and when alpha goes to negative, it goes to this limit. Now, this corresponds to the Rayleigh divergences between zero mid Gaussian measures on Rn. In particular, this alpha equal to 1. This is the formula for the Kn divergence between zero mid Gaussian densities on Rn. And so now we also want to generalize. We also want to generalize this to the infinite dimensional setting. But how do we generalize this? Okay, so let's talk about here. So we need we compute the log pad, and so we have the trace. So we need to talk about the trace class of the. We have a trace, for example, and the log pad is also closely related to the trace. Log pad of H is equal to trace of log A. Now, if we have the covariance operators, which are trace class operators, so basically, if I self-adjoint and come back and it has infinite many eigenvalues, and they belong to the trace class, if the summation of all the absolute value of the eigenvalues, absolute value of the eigenvalues is less than infinity. And now, so the log pad of A is just equal to trace of log A, the summation of all the log lambda k, so equal to negative infinity. So this is actually not well defined because all the lambda k goes to 0. So this is negative, so it's not well defined. So we need to consider like the set of operator A so that we can and that we extend the function, where we extend the function trace and determinant so that its quantities will become finite. And so one way to do it was actually this is what is inspired by the kind of the extended Schmidt norm. So we can also define the extended trace class operators and extended trace as well. So we can define set of A plus gamma I, where A is belong to the trace class, so we can define the extended trace to be trace of A plus gamma. So the trace of the identity here, the trace of identity operator is equal to infinity. But if we define this form in the extended trace is equal to 1, And we have something classically called the Fredholm determinant, the determinant of A plus gamma R, A plus I, where I is an summation of the infinite product of 1 plus lambda k. So this is always well defined, but we also want to define the determinant of A plus gamma I as well. So it's given in this form here. So we're kind of extending the Fredholm determinant to the case when gamma is not equal to 1. So now, if we do this, then we can have an infinite dimensional formulation for the alpha log net divergence. Is given by this formula. This is a simplified version actually, because I said like here we have gamma I, gamma here, because in general this one is like mu I, so it's the formula is more complicated. But in the finite dimension, in the setting when these two we have gamma I here, then the formula looks very similar to the finite dimensional case. It has the same, basically a very similar form. And so if we do this, then we can also have a closed sum formulas in the RKG setting. And then actually there's also related work in the finite dimensional setting in incumbent provision. So some people have been, some people actually have done some work around using kind of these divergences in the finite dimensional setting. And so what does it make any sense? Now, does it make any sense to do this? We have all kind of this extended trace and so on. Does it make any sense? So we can show that we can show how it actually. So this is we can show how it's actually related to the Rayleigh divergence and the Quebec-Labrador divergence, the exact Rayleigh divergence and the Quebec-Labrador divergence of the Gaussian measures on the Hilbert space. Now on RD, two Gaussian densities are always equivalent, so that they have the same support. Now if the dimension is infinite on the Hilbert space with infinite dimension, two Gaussian measures are either equivalent or they are mutually singular, so they have disjoint support. So this is the famous theorem. It's called the Feldman-Hartrich theorem. And if they have disjoint support, then the KR divergence is equal to infinity. So it's very different from the finite dimensional setting, because in the finite dimensional setting we have a closed sum formula and everything is always finite. This formula, the KR divergence is always finite. We have two Gaussian densities. It's not the case in the infinite dimensional setting, but we can show now that if we have two equivalent Gaussian measures on a Hilbert space, and the covariance operators are related by this. Written by this formula, then when gamma goes to 0, then the log net, for example, the case when alpha equal to 1 between C plus gamma I and C0 gamma, it's just equal to the twice the KR divergence between these two Gaussian measures. So we recover the KR in general the Rayleigh divergence between two equivalent Gaussian measures when the regularization parameter goes to 0. So this is a form of regularization, because we are trying to compute like so instead of the KR divergence, for example, we can compute with the regularized KR divergence. And in the case they are equivalent, then when the regularization parameter goes to 0, we recover the exact divergence. And in the case when not equivalent, then the divergence is equal to infinity. And here is expressed in terms of log net 2, because this one is something called the Hilbert gamma determinant. It's defined for Hilbert-Schmidt operator A, given by this formula here. Okay, so that was and this formulation for our divergences can be generalized quite substantially. So we have something called the alpha beta log net divergences, and it can be defined not just for just class operator, for positive just class operator, in general for positive Hilbert-Schmidt operators, as well for the whole kind of manifold. And in particular, it involves the distance the divergence is actually it encompasses the alpha log net divergence I talked about just now, and also the phi invariant Riemannian distance. And they all induce the phi invariant Riemannian metric, so they all induce the same Riemannian metric. So that is so that was the Riemannian distances and divergences. Now, I will talk about the optimal transport distances. So it's in a different, in a slightly different setting. So before actually, kind of the distance and divergence are very closely related. Actually, they have like different formulas, but they're actually closely related. In particular, as I said, like this alpha log net divergence and alpha beta log net divergence all induce the phi invariant Riemannian metric. So now let's go to the setting of optimal transport distances. between probability measures. So this now is a hot topic in machine learning. It was a huge topic in mathematics. Of course, it has been studied a lot. So let's talk about, I will just talk about the Gaussian setting. It's a very simple setting, just nothing extra. So let's suppose that X is a nice metric space. So let's say X is an Rn. Let's just talk about Rn. And then C, X plus X, R greater than or equal to 0 is the nice cos function. So let's talk about the case of least square function. Okay, just consider the case of least square function, X minus Y non-square on Rn. And so let's suppose that X is a set of probability measures from X. So the optimal transport problem between two probability measures, mu0 and mu1 of Dx is given by this formula here. So we just minimize the cos function C according to a joint measure between mu0 and mu1. So the CXYB gamma XY here. So new gamma here without the joint mu0 and mu1, where mu0 with the set of joint probability is much than mu0 and mu1. And now on the set of probability measures with finite moment for the P, but the Vp of x0 x here, v is less than infinity, then then there's something called the P versus time distance. So just given by this OT quantity here to the power of 1 over P. And so this defines a metric on this set of probability measures, and it takes into account the temperature of the underlying space X, via the distance P on the space X. Now in the Gaussian setting, it's actually quite nice because let's consider two Gaussian measures on Rn with M1 and C1, MICI and square cos function. So we can compute the Gaussian formula for this the two versus time distance. So it has the Gaussian formula. It was worked out by various authors a long time ago. And in the case when the means are the same, we have something from the Rbhs versus time distance between SPD matrices. So it's given by this formula here, and it has been also studied. It has been also studied a lot in quantum information theory to measure the fidelity between two quantum states. So in quantum information theory, we have the density matrix, which are SPD matrices with norm with the trace equal to 1. So this is also has a Riemannian structure. It also has a Riemann. It also comes from a Riemannian metric if you assume that the metrics, the covariance matrices are all strictly positive. So the metric is given by this formula here, and the distance is the length of the following geodesic. So it also has a nice and close form formula. But note that this distance here is in the general case, so C0 and C1 is anything. Do not have to be strictly positive because the trace is always well defined, even if they are singular. So this is the difference between the versus time distance compared to the Fisher-Rao distance or the log-related distance we talked about before all the divergences. Because before everything had to be strictly positive. Now with this distance, they don't have to be. The matrices can be singular. Now, so the nice thing about this versus time distance is actually in the infinite dimensional setting, the formula is the same. The formula stays the same because the trace is always well defined. We don't have to take the log, or we don't have to take the inverse, and so we don't have to do any regularization for that. Just everything is actually nice defined, and then so it has been kind of applied. We kind of study in the Gaussian processes as well. As I mentioned, this Rbhs versus time distance between two covariance operators is also valid for singular covariance operators as well. Okay, it has this, of course, it's not perfect because it has some not desirable properties. For example, it's not coefficient differentiable. So now let's move to the next topic, which is entropic regularization of optimal transport. So in the exact optimal transport problem is generally computationally demanding, and the exact versus time distance can have bad sample complexity. So it can be exponentially bad, actually. It has been demonstrated by various researchers. So this formulation called entropic regularization, instead of computing just minimizing just the expected value of C with respect to gamma, we also add like the k-on divergence between gamma and the product measure of mu and nu. So this one is actually the kind of the mutual information between mu and nu. And for k-on is a correct level of divergence. And so this can be solved efficiently. And it turns out that it also like gives actually quite nice properties of the distance as well. In general, when we add this term here, it kind of this OTC here become kind of biased because actually the OT epsilon between mu and mu is no longer equal to 0 in general. So it's not a distance actually, or divergence. So that's one way to do is kind of debiasing. So it's instead of just like OT epsilon, we actually minus like a half of OT epsilon mu and then plus OT epsilon mu and mu. So this one would now become a divergence because it's guaranteed that S epsilon like mu is equal to 0. So this one is called the Synchron divergence. So it has been studied a lot recently. So in the Gaussian setting, let's see how it works out in the Gaussian setting. So in the Gaussian setting, we have, so the formulas was worked out by various authors actually less than 2 years ago. So now with the square function, with the square loss of the square cos function and the two Gaussian measures in Rn, let's look at the KL. This quantity here, KL divergence of gamma, and then mu 0 product of mu 1. This one is the mutual information. So it's given by the H mu 0, H mu 1 minus H gamma, where this H here is a differential entropy. So we have this property called the maximum entropy property of Gaussian density. So if X has mean 0 and covariance support occurrence logic C, then the differential entropy is maximum when X is Gaussian. And so for this quantity to minimize, we need this to be maximized. So it has to be, so the minimizer has to be, the minimum gamma has to be a Gaussian density, Gaussian. And so based on the maximum entropy property of Gaussian density, the minimizer gamma has to be a joint Gaussian density of mu 0, mu 1. And so we have like we have a very clear an explicit form for gamma. It's given by this formula here, and this is the mutual information with the Theorem divergence is given by this formula here. So if we plug everything in, we can solve for this problem. And we have the first formula. This one is for the OT epsilon, and this one is for the Synchron divergence. So they have closed form formulas. So this one actually it involves the n-dimension and in dimension n here, but in fact actually it's actually it turns out that we can show that it's actually dimension independent as we move to the infinite dimensional setting. So that is the finite dimensional setting. So here we have used the maximum entropy property of Gaussian densities. So now let's move to the infinite dimensional setting. So now we encounter something here. Now we talked about the determinant, the log length before. This quantity is no longer well defined because we have an infinite determinant here, and all the eigenvalue will be 0. So it's actually not very well defined. And so if we have like the joint Gaussian measure gamma here, for example, we had the same form as before, but before we have like the Theorem divergence of gamma with mu 0 mu 1 is given by this formula. This formula is no longer well defined in the infinite dimensional setting, as I said before, because of the infinite determinant here. But this mutual information is the Theorem divergence between gamma and mu 0 mu 1 this is always well defined. It can be infinite, but it's always well defined. It's always finite if gamma is absolutely continuous with mu 0 times mu 1. Otherwise, it's infinite, but it's always well defined. And it can be shown that you don't have to worry about the the math here, except that so in the infinite dimensions setting, we can no longer talk about the maximum entropy property. What we can talk about is the minimum mutual information. That's what we can talk about. So suppose that we have like gamma 0 here is a joint Gaussian measure of mu x and mu y, and gamma just another joint measure of mu x and mu y. And so if they have the same covariance operator, then this quantity is always greater than this quantity, and it's given by this formula here. And equalities happen if only if gamma is equal to gamma 0. So the mutual information is minimum for joint Gaussian measures. And where this V here basically this operator V here just relates with the covariance operator of gamma, and gamma 0, where gamma 0 is the covariance operator of this joint Gaussian measure gamma 0. And so as in the finite dimensional setting, now with this minimum mutual information, we know that this has to be, because we are doing minimization, so the minimizer has to be a joint Gaussian measure. And then if we plug this formula in, we can solve for this optimization problem. So this one is an infinite dimensional optimization problem metric, but it can be solved explicitly. We can solve that up, and we can obtain the solution. And a different way to do it is something called we can solve something called the Schrodinger system. So that we can solve the nuclear density of this gamma here, and so we can there are at least two ways to solve for this. To solve the solution, to find the solution. And so, okay, so this is the solution here. So the we can have a closed form formula for the minimizer gamma as well. And with this gamma, we find the synchron divergence. It's given this formula here. So it's actually basically it's equivalent to the dimensional thing in the Euclidean setting, except that the determinant here is now is an infinity determinant. It's a Fredholm determinant. And so when gamma goes to 0, when epsilon goes to 0, so we recover the exact Wasserstein distance. And when epsilon goes to infinity, we just recover this mu0 minus mu1 squared. Okay, so now we can solve we can have closed form formulas for the Wasserstein distance and for the entropic version of the Wasserstein distance and the synchron divergence. As before, we can do it in the RKHS thing as well. In the suppose we have two measures, probability measures rho 1 and rho 2 on X, and they will induce like two Gaussian measures. Before we introduce like the RKHS mean vectors mu and then C, so we can divide the synchron divergence between these two Gaussian measures. And empirically, suppose we have to data set X and Y sample from these two measures, and we can also compute the empirical synchron divergence as well. And so basically, so it gives like if we have a characteristic, then basically it gives like a semi-metric synchron divergence and semi-metric between the two program measures. Now, so this is the formula here. It looks horrible here, but it's just a formula to show you that we have a closed form formula for the in terms of the Bragg matrix. And when epsilon goes to infinity, we just get the maximum mean discrepancy. So this the distance squared between the two RKHS mean, and then when epsilon goes to 0, then we have the Turner versus time distance, the square of the Turner versus time distance. And so it's an interpolation between the maximum mean discrepancy and the Turner versus time distance. So this is one way. So actually, it was actually applied. This kind of versus time distance was actually applied in for commutative vision actually in the book in the visit book. So that is one way to compute this empirically. Now I want to talk about the next concrete computation, which is kind of the distances and divergences in Gaussian processes. It was before it was a kind of the RKHS covariance. So let's talk about the question. Let's apply it to Gaussian processes. Suppose we have a nice complex matrix. Let's say the interval from 0 to 1, and mu is a nice probability measures on T. So the Gaussian process CT here indexed by T is a collection of like random variables, a collection of random variables CT, mean function mu and covariance KST. So KST is given by this formula, and mu T is given by this expectation of the CT. And so for each finite set X in T, we have a random vector C Xj indexed by Xj. So this is a random vector in Rn, and it's distributed according to a Gaussian measure. So it has like the mean here and the covariance matrix Kx here. But it's Kx, just the gram matrix defined on the set X. And so now, let's assume that this function mu t here is square integrable, and then we have dt here, d mu t less than infinity, so kind of similar to before. So according to result as Rajput and companies a long time ago, 1972, this formula is sufficient and necessarily sufficient for the following. The sum parts of CR in L2 d almost surely, so they are square integrable almost surely. And that's a one-to-one correspondence between the Gaussian processes GP mu k measurable, and the Gaussian measure would mean mu and covariance operator CK on the Hilbert space H equal to L2 with the covariance operator, just integral operator with the kernel K. So that's a one-to-one correspondence between Gaussian processes and Gaussian measures. And so what has to be, well, this is also a classic, so what has to be careful, but if the dimension HK is equal to infinity, then the sample parts are actually outside of HK or both surely. So they do not lie in the RKHS, that should be like outside the RKHS, but they are square integrable. So now we can actually think about the Gaussian processes. Actually, we are kind of sampled from these Gaussian measures on L2D new. We are sampled the function CT on based on this Gaussian measure on L2. And so now with this correspondence, we can define a Gaussian distance of divergence between the Gaussian processes and distance of divergence between their corresponding Gaussian measures. So there has been a lot of work actually studying the distance of divergence between Gaussian processes. So let's consider the case when we have for simplicity, let's consider the case when mu is equal to 0. mu1 and mu2 is equal to 0. So then we just have the distance of divergence between zero mean Gaussian processes or zero mean Gaussian measures. And so we can define, like for example, the log Hilbert distance, we can define this as log of gamma I equals ck1 minus log of gamma I ck2 with the extended Hilbert norm. We can define the fine variant remaining distance. We can also define the versus time distance and the synchron divergence. So these are, of course, this ck1 here and ck2 here are infinite dimensional covariance operators. So now we want to estimate them. We have to estimate them from finite dimensional versions. So now if we have like a finite set of x here, so this is m in T, and then we have then this vectors we have CISRIKEN here, just distributed according to the Gaussian measures with zero mean and covariance measures kx. So we want to be able to estimate this infinite dimensional formula from the finite dimension using kxi. So it turns out that we can estimate them consistently by the finite dimension by the distance of divergence between the Gaussian measure with zero mean and also the covariance, which is 1 over mk1x. 1 over mk is equal to x for all of the distances and divergences we have talked about. So now, so these are quantities in Rm because this actually here it's a matrix of M by M, so it maps Rm to Rm, whereas this actually map L2 to L2. So they are not exactly in the same space. They are not operated in the same space. So it's not straightforward actually to compute the divergence. So what we employ is something called the RKH. Because we're actually working with this K1, K2 here kernels, and so they have corresponding RKHs. We can define RKH operators as well. So what we are going to do, we are going to prove the convergence using RKHs operators. Okay, so maybe I would just go over this briefly because this one is a bit advises too much information. Okay, so we can define the operator like kind of the RK for example, L2 to HKI. RKI can do this formula here. So it's quite similar to the so let's listen to this. So CKI just which is RK transpose time RK, but this RK transpose here just the inclusion operator. So CK is given by RKI transpose and RKI. We can also define the cross covariance operator. RKI from RKJ transpose. So it maps HKJ to HKI, and we can define the RKHS covariance for the LKI to RKI from RKI transpose. So these two will have actually they look very similar, but they map onto different spaces. So basically, we will transform quantities using CKI, mapping from L2 to L2 to quantities using LKI, and also RHS map from RKHS to each other. And we can also, so now these operators actually they have a lot of things come on. They have the same non-zero eigenvalues and the same traits and the same number split norm, etc. And that's the same when we restrict them to this, the space HKI. But in general, they are actually not interchangeable because we can define the distance between and 0 CK1 and 0 CK2. This is well defined, but this one, for example, 0 LK1 and 0 LK2 is not well defined in general because they belong to two different spaces. LK1 and LK2 in general, they operate on two different spaces, so they're not well defined. And then you can also define the empirical version as well, based on data set X. Okay, and in particular with the RK I on a set X here, it has the same zero eigenvalues as the matches one of the MKIX. So we have this one of the MKIX here, apply it basically has the same zero eigenvalues as MKI. So we can represent basically the quantities using one over KIX instead of in terms of MKIX. Now, so with this cross-covariance operator here, they can we can apply the law of large numbers for Hilbert space value random variables. We can show that they actually the empirical version will converge to the theoretical version with high probability. So now, in order to do this convergence, we need some form of some form of convergence in some norm. So one nice thing about the Shinhan divergence and also the Hilbert-Schmidt and the phi invariant distance, such that they converge in the Hilbert-Schmidt norm. So here, for example, this is for the Shinhan divergence. So if we have two covariance with a sequence of covariance operators AI, if they converge to A in the Hilbert-Schmidt norm, then we have a convergence in the Shinhan divergence. Now, this is not the case with the Wasserstein distance. The Wasserstein distance converges in the chess class operator, chess class form, which is actually a stronger condition. We need a stronger convergence for the covariance operator for the Wasserstein distance to converge. And so this actually has some consequences that we'll see later on. So if we put the Hilbert-Schmidt norm, we can apply laws of large numbers for Hilbert space Hilbert space value random variables to obtain sample complexity. So so let's see now. So here we transform instead of we have like this Shinhan divergence here, for example, between operators in L2 and in Rm. So here we transform them into RKHS operators, mapping from HK1 to HK1, HK2 to HK2, and then HK to HK2, and the same thing here. So we have like quantities defined on the same spaces, so we can actually compute the convergence here to here, convergence here to here, convergence here to here. So this is actually how the convergence is done, and we can show that the empirical version converges to the theoretical version with high probability, and the convergence is dimension independent. And we can do the same thing for the Lockheed-Schmidt distance and the phi invariant Riemannian distance. The technical details are different, because they are different distances, so we have to have different kind of representation using the RKHS and covariance and cross-covariance operators. But kind of the idea is basically quite similar. So we have the same kind of sample dimension independent sample complexity, just the empirical version converging to the theoretical version. Now, this is different with the Wasserstein distance because of the chess class, because we require the chess class convergence for the Wasserstein distance to converge. So actually we cannot apply like and the chess class norm is actually like a Banach space norm with type 1. So it's I'm not aware of kind of like very good convergence results, like good law of large numbers for the chess class norm. So for the moment, I can show that the empirical version converges to the theoretical version, but only in the case that at least one of the RKHs has a finite dimension. Otherwise, we can have the convergence, but not the rate of convergence. Okay, I would probably skip this because it's kind of too much. Because just to say that we can also. If the finite covariance matrix KX is not known, then we can also estimate KX from finite samples as well, but this is not okay, we'll speak this. We can just show that if we estimate the sample covariance, the covariance matrix is the finite covariance matrix from the sample data, we can also arrive to the estimation of the exact theoretical version. And here, the dimension, the convergence is also dimension independent. So let's see a little bit, a few examples here. So here we have on the left-hand side here we have like two Gaussian processes. Here we have the covariance here is just negative a to the times on the interval from 0 to 1, so x minus y absolute value a equal to 1. This is actually very familiar example of Gaussian processes. And on the right-hand side we have the Gaussian kernel. And so the paths are very smooth. And here we show the Gaussian divergence. I'm sorry, the phi invariant and Hilbert-Schmidt distance. So they both converging to some value here. And the same thing, now here I'm trying to simulate Gaussian processor. We have the same, very similar kind of covariance function actually, so that we have, so A here is equal to 1 and A here equal to 1 minus 1 over 2. So they are much closer to each other. And so we have, we are converging to a much smaller value, as we should expect. And here are the example of the Weierstein, the Hilbert-Schmidt, and the Singhorn divergence of the Weierstein, Hilbert-Schmidt, and Singhorn divergence. So here we have the interval from 0 to 1 to power d, where d equal to 1, d equal to 5, and d equal to 50. But see, we can see that here for the Weierstein distance, we can see that actually we do not have the dimension independent sample complexity, because they have like different behavior with the dimension increases, but whereas the other one actually have very similar kind of behavior. So, so as I said, like I do not have the convergence rate for the Weierstein distance when both of the RKHs have infinite dimensions. And I think the dimension independent convergence for the Weierstein distance doesn't exist, because this is judging from the empirical values. Like, so to summarize, maybe there's a lot of material. So we'll talk about the generalization of the Riemannian distance between Gaussian measures of Maranko, the Hilbert-Schmidt setting, and then we talk about the phi invariant Riemannian distance or the Fischer-Tropsch distance, the log Euclidean distance, the log determinant divergences. So in this, for this distance and divergence, the regularization of the covariance is theoretically necessary. And we talk about the Weierstein distance and its entropic version, and we can see that with the entropic regularization, it leads to some very nice theoretical properties, such as example dimension independent sample complexities. It has some other nice properties as well, apart from this dimension independent sample complexity, and many more theoretical results can be put as well. And I'll have some upcoming work with the on the Kullback-Leibler and Renyi divergences between Gaussian processes. Actually, I have just completed the manuscript, so it should be available on the guide pretty soon. And future work we have to move beyond Gaussian processes. So I'm sorry that the talk has been kind of entirely theoretical, mathematical. That's not, I haven't really shown you any application here. So hopefully in the future, we have like practical applications as well. Or if you have like some applications, I would love to hear about them. And so here are some of the kind of the latest references. So we have some kind of papers, some are still in review and some have already just been published. So this is the end of my talk. I would be happy to take any questions if there are any.
Thank you very much for this talk. I mean, this is fantastic, actually. Now, if the attendees have questions, please use the Q&A box. I just would like to ask a couple of things. First of all, this is almost like a cheat sheet for me, that it would be great to have access to your slides.
Sure.
This was very, it's a good compilation of these metrics and their implications. So I very much appreciated this work. And you also mentioned very interesting things about the Singhorn, the smoothed Weierstein distance with the entropy, the Singhorn having very nice theoretical properties and dimension independent. I mean, do you think that these kind of things can also be used? So let's talk about applications, as you mentioned. In generative adversarial networks, we end up trying to minimize, for example, the Weierstein distance of an empirical measure with respect to a push-forward measure defined by a neural network. Now, there, the dimension is actually a curse, right? Because you don't have access to the true measure. You end up working with the samples, and there's a terrible dependence between the distance between the empirical samples to the true measure. Now, do you think that you would gain advantages with the smoothed Singhorn kind of distances there? Do we get any advantages in analysis that you can think of?
I would expect so. I would expect so. Well, it's not clear until we do it actually. So it's not, we cannot really say for sure unless we actually do the actual experiments. But I would expect so. And I think I'm not quite sure whether somebody has tried it.
And there must be, yeah.
I think
there are also some experts in the audience, like I think Taiji is in the audience.
Right. I think somebody probably has. Maybe it has been. I don't know. I have to check actually, because I have not done I have not really kind of done any experience about that. So I think I think we have to do it to really know actually whether it really does help in.
Because actually in optimization, it also does help the smoothed, because then you have a differentiable distance.
Right.
And yeah, I mean, so yeah. So
it becomes much nicer actually with the entropic regularization, because it becomes like also like strictly convex, and also like the very center problem actually becomes like much better well defined actually. And,
actually, that is correct, because I remember Marco Cituri had this work on smoothing with the entropy and then running the accelerated gradient method on the primal problem to gain computational advantages. So there are many things that we can do. Like I think very interesting set of I would again not to diminish anything, but it's like a cheat sheet of you know, like good distances and where to find them. You know, it's
right.
It's very nice.
Thank you.
So is there any questions from the audience?
So I have a naive question. So
sure.
let's take the first paper here. So
which one?
Infinite dimensional Gaussian measures.
Oh, okay.
For Bastian-Stein distance. So how do you really compute in practice? So I still didn't really get that part.
Oh, so for example, like with this Gaussian, if we have like the Gaussian measures which are corresponding to Gaussian processes, for example, we can compute using using this approximation, for example, like finite dimensional version here. We can so if we know K1, so if we have so for each Gaussian processes might correspond to, we have a one-to-one corresponding with Gaussian measure, right? And then if we know the covariance matrix, for example, on a finite set X, we can compute the empirical version. So this is like a consistent approximation of the theoretical distance.
So basically, computation is done in like an empirical kernel space, even though the entire space is infinite dimensional.
Right. So practically we cannot compute the because we do not know actually in fact we do not know the covariance, like the exact covariance operators. We do not know them. So we have to compute. If we know them exactly and we know all the eigenvalues, then we can compute because we have the exact formula, so we can compute like the trace. For example, I'm sorry. Let's go to the formulas. We can compute like the trace. If we know all of these exactly, we can compute their eigenvalue and so on. Then we can compute like the trace and so on, and the log determinant and so on. But in general, we do not know them like analytically, right? So we have to compute them practically. We have to use estimation. So empirical estimation.
Empirical estimation.
Right. Empirical estimation. But actually, with the sample convergence, for example, they have like dimension independent convergence, so they all converge actually kind of nicely, I think. But of course, we have to see how they can actually will work out actually kind of in real situations. Because here, like we kind of here the synthetic examples, because I assume that I know the covariance function. Well, we can if we have like sample data, for example, we can also compute using sample data. But we have to estimate the covariance function, of course.
So in high level, so empirical approximation is usually used for like converting the true expectation to empirical average. But in this case, also it converts infinite dimensional calculation into finite dimensional calculation.
Right. So we have the convergence, right?
I see. Yeah, thank you. That's clear now.
Right. So we always have to start from the finite dimensional setting actually, because because there's always like a limiting process actually when we do the computation. There's always a limiting process from the finite to the infinite dimensional, because really we cannot compute with the infinite dimensional setting. We cannot, like practically we cannot compute.
Thank you again for the answer. Like I said, it would be great to have access to these slides somehow.
Sure. I think we can make them available. I can send you personally as well. I can send you. Thank
you. I will make it available to EPFL community at least.
Sure.
So, anyway, the talk video and slides will be open to public.
Oh yes, on the RIKEN site, no?
Right.
Fantastic. Okay, so I think this concludes our talk for today. Thank you, Min, again for this fantastic talk.
Thank you very much.
Everybody for joining in for this talk. Have a great evening in Japan and have a great day in Lausanne.